When we talk about bicycle tires and how much air you put in a bicycle tire, it's very dependent upon the type of tire you're on. So when you climb on a bike, your force, your weight is going to be pretty consistent. Now, give or take, the frame of the bike might change when you change styles of the bike, but let's just pretend it's the same. But your force is going to be the same. But you put different pressures in your different amount of pressure in your tires, depending upon the type of bike you're on. And the reason is, if you think about the tires themselves, what's the difference between a fat tire bike and a mountain bike and a road tire bike? Do we know the difference between these? Is one thicker than the other?
Yes.
Which one? And what's bigger than a mountain bike?
I don't remember the other one.
Fat tire bike.
That one.
Yeah, that one. That one's bigger, right? So the idea is, if you are on a fat tire bike, there's physically more area, the tire is wider, that's in contact with the ground. A road tire bike is a very thin, narrow tire meant for pavement and pavement alone. Now, why would you want a fat tire bike tire? Because you're going through like mud or snow that's pretty soft and squishy, and you need some of that for traction. A road tire bike is meant for paved roads, and you want to go fast. So every year I would ask Mr. Poofall, but he's not here to ask that question anymore. How many PSIs of air do you put in a road bike tire? And I don't remember. I think it was like 80 PSI. So your car has right around 30, probably right around 30 to 35. 28 to 35 would be my guess, the range of most of your car tires. And a fat bike tire maybe has 15 PSI. So depending upon how much surface area you have in contact with the road, depends upon how much pressure you need to hold that tire up, so when you are riding your bike, you're riding on the rubber part of the tire and not the frame of the rims. So, we can look at that. Right at the end of class yesterday, I was starting to talk about hydraulic cylinders. So here's an example of a hydraulic cylinder. So a hydraulic cylinder is a way that we could increase, or decrease, I guess for that matter, the mechanical advantage of an object. So and I should change this to make this more. There, that's more obvious. So if we were to say that is that. Okay? So my picture shows a cylinder that if I push down on the little cylinder, what's going to happen is my big cylinder is going to get pushed up. Now the reason for that is because when I exert a force over some area, and that's kind of cross hashed, that over some area, I create some pressure. If we're calling it F1 and R1 and A1, we're going to create a P1. We're going to create some amount of pressure in this cylinder right here in the liquid. So by me pushing like that, I'm creating some amount of pressure. Now, in there is water. It's colored water. And what's true about water? Is it a compressible fluid or an incompressible fluid? Can I take a water balloon and make several water molecules closer together? No. So water is an incompressible fluid. Okay. Can I take air and press air molecules closer together? Yeah, it's a compressible fluid. So, because I have water in there, it's an incompressible fluid. So what happens when I exert a downward force here? Well, it pushes down here, and then it hits this turn, and then it pushes this way, which then pushes this way, which then causes that to go And if I were to take a pressure gauge, and if I were to attach it right here, and right here, and right here, this is what we consider to be a closed system. We could measure the pressure at location 1 and the pressure at location 2 or 3 or 4 or any point along the way, but because this is a closed system, that when I push on these two things, we would actually find that the pressure in the fluid are actually equal to one another. So P1 is equal to P2. We could say that the pressure right here, because I pushed down on the small cylinder, is equal to the pressure right here that's pushing up in the big cylinder. Okay, so let's take a look at problem number 3 on your worksheet yesterday called in-class pressure, density, and pressure at depth worksheet. So the measurements here are meant to be kind of close to this thing right here, just for illustration purposes. So if I had a 20 Newton force, this is number 3. If a 20 Newton force is applied downward on a hydraulic cylinder that has a radius of 0.5 centimeters. So if we take a look at this small cylinder, I'd say that's about 1 centimeter in diameter, therefore my radius would be about 0.5 centimeters. Now our numbers need to be in meters because my area needs to be in meters squared. So the conversion as we shift the decimal point 2 times would be 0.005 meters. It was here, we go 1, 2. Okay? If a 20 Newton force is applied downwards on a cylinder that has a radius of 0.5 meters, with what force, question mark, does the second cylinder push upwards if the radius is 3 centimeters? So again, it has to be in meters. So that converted into meters is about is 0.03. So close. It's about 5, 6 centimeters. Maybe a little bit big. But that's that idea. So we're going from a small to a large. We're going from a small cylinder to a large cylinder. Now, if my pressure here is equal to my pressure here, remember P is equal to F divided by A, so P1 is equal to F1 divided by A1, and P2 would be F2 divided by A2. If we did a substitution, I can say F1 divided by A1 is equal to F2 divided by A2. So I need to know my area, I need to know my forces, one of which I know, the other which is what we're solving for. And we can figure this out. Now we get some mechanical advantage with a hydraulic cylinder. If we apply a smaller force on a small cylinder and in return it pushes on a big cylinder, we're going to come out with some mechanical advantage. So area at location 1 is a cylinder, so it's pi times r1 squared. So my A1 is equal to pi times 0.005 squared. My A1 my area at location 1 is 0.00001, 2, 3, 4, 7, 8, 5, 4. So I'm going to round it, but I'm going to store that number in my calculator for later. So my area is 0.000079 meters squared. And you say, boy, that's a really small number. You're right, it is. But if you look at like my finger, that's about this finger. This finger is about the same diameter as that cylinder. Okay, So if this is about a centimeter across, then my radius would be about 0.5 centimeters across, right? So remember that this thing is probably going to fall apart. Sure. This thing is a square meter. So if my finger represents 0.05 centimeters, which is probably pretty darn close, how many of these fingers can I fit in this area? And the answer is a lot, right? So is that okay that we came up with a really small number? Realize, yeah, that this is a big thing. This is 1 meter squared, and this is like a really, really small portion of that. Okay, so you can say, well, I don't know if I got that right. It's gonna be a pretty small number because 1 meter squared is a pretty big area. Then we can go through and say, well, A2 is pi times R2 squared. And A2 is equal to pi times 0.03 squared. So my A2 is equal to another number. Now this is going to be a less small of a number, but it's still going to be a small number. So this number is 0.002827 meters something squared. Okay, so now I have my two areas. So I have my area 1. Store that to use my calculator for later. So I have my area 1. Area 1. I have my F1. I have my area 2. I should mathematically be able to solve for F2. So F1 was 20 divided by the area of 0.000079. Now there's more digits in my calculator, and I'm going to use my stored value to get a less rounded value. And I divide by my A2. Most people would choose to cross multiply and divide this, which I would also choose to do. So you're going to take 20 times 0.0028 equals 0.000079 F2, divide by 0.000079, and we should get a value of F2 to be 720. So if I push down, now this cylinder is probably a little bit too large to represent this cylinder. This is probably not 6 centimeters across. This is definitely not 6 centimeters across. This is more like 3 centimeters in the radius, or diameter, so it's really more like 1.5. But the idea is if this were the case, if I push down with 20 here, it pushes up with 720. That's a pretty significant mechanical advantage or mechanical gain. And this will be here, you're welcome to play with it. I think I mentioned this yesterday. Just if you don't clamp on the wood, don't grab the syringe, just push on the plungers, because then we should be within the threshold that could withhold. But it's always kind of fun to like push down and this, and when like try to hold it down and they push really hard on their thumb and you just go whoop with like one finger and they're pushing with their body. It's a way we can increase mechanical advantage. Now with heavy machinery, not only do we use hydraulic cylinders, so we can use a pretty small circulating pump to pump this fluid. Now incompressible fluids are the best. Water, oil, hydraulic oil, brake fluid. And we can create some mechanical advantage, but in addition to this in like heavy equipment, then we use other simple machines like levers, and we create lever arms where we can increase our mechanical advantage even more. But wood splitters use this idea. A small pump can create a relatively large force if we go through and we get a fairly large cylinder pushing against like that wall. So we can create a fair amount of force. So some of those log splitters, I'm trying to remember, they might be like a 20 ton or 35 ton, I think are the numbers that I've seen on those things, of force that they can push forward in order to split those logs open. So it's a way that we can increase mechanical advantage, and it's a pressure thing, is what it ends up being. The next kind of piece of this section is dealing with density. So density, we use this really cool letter. It's the Greek letter rho. Chemistry, they use a capital letter D. Oh, how cute. We use Greek letter rho for density. So it comes down later. But it's on your formula sheet. It's this. On a computer, it's kind of almost looks like an italicized P. But it's a Greek symbol, it's a Greek letter, and it's referred to as rho. So rho, kind of a curved P, is equal to m divided by v. So this is density. This is mass. And this, I'm sorry, m is mass, rho is density, v is volume. Now there's lots of different units you could use to measure density. There's lots of different units you could use to measure density. Depending upon the units you use for mass and you use for volume is what really dictates the density units that we use. In this class, to make our formulas work out, we have to use, and we've been pretty consistent with mass all year, being measured in kilograms. Even when we use the electronic balances, we have to convert it in our calculations to kilograms. Still the case. And our unit of volume kind of follows our unit of volume up here for area, but instead of volume, area is like base times width, or length times width, where volume is length times width times height, so it's a three-dimensional object. So this is not meters squared, but it's meters cubed. And if you take kilograms and you divide by meters cubed, you get a unit of kilograms per cubic meter. Per cubic meter. Now in chemistry, I think the units they used were grams per milliliter, which is fine. It's a unit, it works. As long as all your units are consistent, that's the key. But the formulas that we use this value in, this doesn't work out. So in chemistry, when they talk about like gas laws and whatnot, it works out fine for them, but it doesn't work out fine for us. So these are the units we need to use. Now, that cube that's sitting on the table, pretend like those aren't, that top arm isn't bent. That's 1 cubic meter. So 1 cubic meter is 1 meter by 1 meter by 1 meter. That's a little bit better. And pretend like those are not wobbling and bent out. That's 1 cubic meter. That's pretty big. Okay? That's pretty big. So when we talk about the density of something, we talk about how many kilograms of that item would fit into that 1 cube. Some common units that we use is we talk about the density of water. Now when we talk about the density of water, there's different types of water. And I'm not talking about like Kroger brand of water versus like Fiji water. I'm talking about fresh versus salt is kind of how we classify those. So when we talk about fresh water, we're just referencing non-salt water. And then we have salt water. Now the difference between those is because there's physically more stuff in salt water. There's salt in it. So it changes the density stuff. But if we talk about fresh water, so Lake Wausau is fresh water because there's no salt in it. The density of fresh water is right around 1,000 kilograms per cubic meter. So if I took that cube and I filled it with water, we can measure the density. So 1 cubic meter of water would have a mass, because it's mass divided by volume, so if my volume is 1, the mass would be 1,000. cube were full of water, would you be able to pick it up? Would you be able to carry that? No, you wouldn't. Because water is very heavy, it's very dense. It's about 8 pounds per gallon is kind of what the number we often use. But this is 1,000 kilograms, and 1 kilogram on Earth is about 2.2 pounds. So if 1 kilogram is 2.2 pounds, that 1,000 kilograms of water is 2,200 pounds. And they refer to that as a metric ton. So if something has a mass of 1,000 kilograms, they refer to it as a metric ton, which a metric ton is 2,200 pounds. We refer to a ton as 2,000 pounds, but a metric ton is 2,200 because it's 1,000 kilograms. So that cube in the back of the room would weigh 2,200 pounds and probably break my table in the process. So we can talk about density. Now, different substances have different densities, and the thing that's kind of interesting is if I wanted to find the density of water, do I have to fill that cube full of water and measure it and then divide it, or can I use a smaller container? Yeah, I don't have to do 1 meter by 1 meter. I could use a smaller container because it's a mass per unit of volume. So if I know what my mass is, however many kilograms, and if I know what that volume is, now in order to get my units to work out, I'd have to convert that volume into cubic meters and figure out how many of those water bottles fit into there. There's conversions for that. But I should get the exact same value of 1,000, whether I do the whole thing or the small. And the thing about density that's kind of interesting, I find it interesting at least, is that's the idea, that's the story behind who is it? Archimedes. Archimedes Presley. Yeah, and that was the crown, right? The crown was Archimedes, the king's crown, running through the streets yelling "Eureka, Eureka." That was Archimedes. Okay, yeah. So the idea that he was tasked with trying to figure out, like, is this crown made of pure gold or is it some mixture? He didn't have to like melt the crown down into like a block of gold so he can go length times width times height to determine that volume. Because if he knew the mass, pretty easy, set it on a scale, balance, a long time ago. And if he knew the volume, he could determine what the density is. And he could compare that to a known density of gold. The thing that he had to figure out is how do I find the density or the volume of this irregular shaped object, and that's where those overflow cans that you guys use in chemistry from those triple quad beam balances in the string, is this going to cause water to overflow, which then you can go through and you can figure out the volume that it displaced. Okay. So there's a couple different calculations that we could do with these. You know, if I gave you the mass and I gave you the volume, you could find density. If I gave you the force, I gave you the area, we could calculate pressure. But these are just it's an equation. So if I give you these two, you could solve for this variable. But if I give you these two variables, you should be able to solve for this one or these two, right? We should be able to solve, given any two variables in a 3-variable equation, mathematically we should be able to calculate that. So a pretty common calculation that we do with this is calculate density, or the one that's on the worksheet for us to do together, is we're actually going to solve for mass. And once we move on to a different part of this unit, when we start talking about buoyancy and forces again, then this is a fairly common calculation we do. So if we take a look at question number 4 on the worksheet called what is in class pressure, density, pressure at depth. Question number 4. It says, what is the mass of a metal block that has a density of 7,700 kilograms and dimensions of 0.5 meters by 0.2 meters and 0.5 meters? So if we have a block that looks it's trying to figure out how many kilograms is this block if the dimensions are 0.5 by 0.2 by 0.5 meters. The thing that was given is it told us the density of this block is equal to 7,700 kilograms per cubic meter. So it's just solving for a different variable. This time we're solving for the mass. Now, this is not a cube because it's not three equal sides. It's a rectangular prism, I believe is the proper term. And in order to calculate the volume of this, we take base times width times height, or length times width times height, or whatever you want to call it. What we do is we simply multiply the three dimensions together. So I would typically say length times width times height. Our volume is going to be 0.5 times 0.2 times 0. And our volume is then going to be 0.05. 0.05, and our units are meters. So now we know the volume of our cube, or I'm sorry, our rectangular prism. So if our density is 7,700, our mass is unknown, but our volume is 0.05. When we cross multiply and divide, we can then solve for the mass, and the mass of that block is going to be 385. So a calculation like that is going to become fairly common in the near future. So given the density of some object, given the dimensions of the object, you should be able to determine the mass, and then we'll need to use that mass to determine the F and G of that object. Okay, so density is mass divided by volume. So that cube in the back, I said the density, if we were to fill that with water, would have about 1,000 kilograms in there, about 2,200 pounds. Now, what if we were to take this cube and we filled it full of air? Which I already took I took it upon myself to do that earlier today. I filled that box full of air for you. So if I were to put that on the scale, would it weigh anything? Does the air in that box weigh anything? Yes, it would, right? Does air have made up of atoms? Do atoms have a mass? Does air have mass? Yeah, okay. So it does. So if the density of that water, it was 1,000, the density of water is 1,000 kilograms per cubic meter. If we were to fill that with air, now this is kind of a subjective number and it varies some, but it's right around, we often see 1.29 kilograms per cubic meter. So if 1 kilogram is 2.2 pounds, that cube would be filled with 2.5 pounds of air. And sometimes that's kind of a hard thing to see, and you're like, what? How do I weigh air? Like, how do I physically do that? In chemistry, I got a lot of blank looks last hour when I found this. In chemistry, did they use this cylinder at some point with a vacuum pump? Okay, if they use this, what they do is they can push this valve and they open it. Oh, it's full of air. Okay, it's full of air right now. And you can put it on a scale and it'll have some value. So when I find the mass of that bottle, I'm finding the mass of that bottle and the air in that bottle. Okay? Then what they can do, this is a valve. They can open the valve and they can hook it up to a vacuum pump, and they create areas of low pressure, and they can remove as much air as they possibly can, and they can create a vacuum in here, which is really the absence of air. And then they can close it. So if I removed most of the air in here, I create a vacuum, and and then I put it on the scale. The first time I found the mass of the bottle and the air in it. Now, if I put that on there, now I'm finding the mass of just the bottle. Should that bottle be heavier the second time, lighter the second time, or the same the second time? Did I add stuff to it, take stuff away, or did it stay completely the same? Lighter. I took air out, right? I removed it. You could do the same thing with a balloon. If you took a balloon, you put it on a balance, you find the mass, be some number. If I blow up that balloon, tie it, I put it on the balance again, that balloon will be heavier now because I put stuff in it. So when we talk about air, air does have a density, and it does have a mass associated with it. Now, I've said this a few times, when we talk about the density of a fluid, oh no, I haven't mentioned this one. I've talked about a fluid being compressible or incompressible. And when I talk about something being compressible or incompressible, I'm saying, can I push the things closer together, or can I stretch them further apart? That would be compressible. Incompressible is when I try to go like this, nothing happens. Right? So if I were to measure the density of water, like right here in western Wisconsin, and then I were to go to a location of a different pressure. I could go up in elevation, I could go down in elevation, a high pressure front comes through, a low pressure front comes through, something happens. Water is incompressible, so the density of this water would remain the same, it wouldn't change. But air is a compressible fluid. So I can take air and I can push the molecules closer together. I can take air and I can put it at low pressure and I can push them further apart. And by doing so, I change the density of the air. So that cube, depending upon the conditions, will hold more, if we push them closer together, air molecules. Or it will hold less air molecules if we move them further apart. We can do that with temperature. I can heat up temperature, I can heat them up, which then they get further apart, so the density of hot air is less than the density of cold air. So the density in this room is less than the density of the air outside. Air molecules are closer together outside. But we can change elevation, and that's going to be what we're going to reference. So if we talk about atmospheric pressure, there's an amazing mountain that I do. What we have is we have a whole bunch of air molecules around us. And these air molecules that are surrounding us are what create atmospheric pressure. So when we talk about air pressure, if I'm standing, and this is on the beach in spring break, so we are at 0 feet in elevation, we are at sea level. If I was going to look at how much atmospheric pressure I have, basically what I have to do is I go through, and these molecules are pushing down on me on the beach. And every molecule from the upper edge of the atmosphere are pushing on the next and the next and the next, and they combine all together to push down on me, which is kind of a weird phenomenon from the standpoint of I'm inside, and I'm not actually directly underneath those air molecules, but the weight of those are still pushing down on me based upon that. So I have some level of atmospheric pressure here. Here in western Wisconsin, we are at an elevation of around 1,200 feet above sea level. And that's a little too high, but whatever, 1,200. So if I, all things equal, am standing here and I look at all the air molecules above me, do I physically have more or less air molecules here than if I'm on spring break and on the beach? Is there more above me or less above me, everything else equal? There's going to be less air molecules. So because there's less air molecules, my pressure is lower than it is here. And my pressure in western Wisconsin is lower than it is here on the beach. If I go to Denver, which is right around 5,500, let me say 5,000 feet, mile high, there's, again, even less pressure than here in western Wisconsin. So my pressure changes. Now what happens to the air molecules as the pressure decreases? Do they get closer together or do they get further apart? Pressure. If I decrease the pressure, are things going to get pushed closer together or are they going to get pulled further apart? They're going to get pulled further apart. And as we go up in elevation, the common term we use is we say the air gets thin. You've heard of it. The air gets thinner. And what we're talking about is the density of the air gets less. The density of the air gets less. Now, if you keep climbing in elevation, you are now on the top of, say, Mount Everest. I believe, I believe the elevation of Mount Everest is right around 22,000? I think it's 22,000. The air is really, 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 really thin up there. Now, if I was a world-class, high, a world-class endurance athlete, a lot of those world-class athletes, they train in Denver, Colorado. They train in Colorado Springs. They train at high elevations. They choose to train in locations where the air is thinner. Because by training in where the air is thinner, your body naturally responds to that lack of oxygen. So every breath you take, you fill your lungs with air. But if you're in Denver, Colorado, there are physically less air molecules.
Please excuse this interruption. The following 11th grade ELTs are required to attend the course registration process today in the auditorium. Mrs. Joe Bailey, Mrs. Blanchette, Mrs. Buckler, and Mr. Jay Coonan. This is a mandatory meeting and attendance will be taken. And it is your opportunity to pick your classes for next year.
So the air is physically thinner. So when you take that breath and you fill your lungs, there's physically less oxygen molecules in that breath of air. So in order to get the same amount of oxygen in Denver, you have to take extra breaths along the way. But your body's natural response to that is with time, it adds red blood cells. Yes, yes.
Okay, so I'm confused how you got 720 for that problem we did, like number 3. I kept getting like 708.
Yeah, I got 702.
I was like, am I doing my math wrong? I did it like 3 times and I kept getting 7.
Yeah, I got
7.86.
Just round it up. 8 numbers.
Did you use rounded values?
No. Oh, that's probably why, because you had it in your calculator. I didn't. Okay, never mind. Well, that's such a difference in